AP Physics students, this is the winter break homework. I am in the process of, recording these videos and getting them uploaded to PowerSchool, and I'll make a couple of remarks and comments as to how this fits into the bigger picture of what we're doing for the rest of the semester. Beginning with the first problem. So, before break, we looked at differential equations of this nature where we had a problem like dy dt minus 3y equals 0, subject to some initial condition, say y of 0 equals 4. And what we concluded was that the overall solution when we do separation of variables is y equals 4e to the 3t, and when we plug this back into this original differential equation, that's the solution. So we took this and applied this problem to two types of main circuit problem. The first was one where we have a fully charged capacitor with a charge Q naught on it, and at time equals 0, we would close a switch, and the capacitor has capacitance C, the capacitor has a capacitance C, the resistor has a resistance R. At time equals 0, we would close the switch, and what we concluded was the charge as a function of time on the capacitor is given by the following: e to the negative t over RC, where we have a time constant, RC. And similarly, if we have an inductor that has a current I naught going through it, and at time equals 0, we close a switch where it's connected to a resistor. Using this differential equation, separation of variables, we concluded that I naught equals e to the negative RT over L. In each case, in this case, the differential equation we solved was that negative dq dt times R minus Q over C equals 0, which has the form of this differential equation. And here we had that IR, negative IR, minus L di dt equals 0. Again, both of these differential equations follow the form of this equation that you'd see in a calculus textbook, but we have to adapt it to physics. And what we're going to work on today is an application of this in the field of mechanics. So it's going to be a similar solution to what we've done in class, and now we're going to apply this to a problem where it's still separation of variables. It's this form of the differential equation, and now what we're going to see is that this also is something that pops up in mechanics. So an object is moving with mass m is moving along the x-axis with velocity v and is slowed by this force negative kv, where k is a time constant. At time t equals 0, the velocity has this particular value, and we want to know the initial acceleration produced by the resistance force, and we're going to derive an equation for the velocities as a function of time and sketch the function on the axis below, and we'll call right the positive direction. So we'll have a couple of things to do here, and we will go ahead and actually figure that out now. So part A, the initial acceleration. Well, let's set that up doing Newton's law. So we can say F equals ma, and we can say negative kv equals ma. And the initial condition, because if you remember with our differential equations, we always have some kind of an initial condition. And to be clear, the variable that we're going to be solving for using separation of variables is the variable v, just to be even clearer. In our calculus textbook, we're usually solving for a variable like y. In our RC circuit, the variable was q. And in our RL circuit, the variable was I, the current. So just an abstract variable y, the charge q, and the current I. Here, we're going to be solving for the velocity as a function of time. So just to be clear, our initial condition is that v at time equals 0 is v naught. So what that means is that at time equals 0, we can actually do a little substitution here and say negative k v naught equals a. So our initial acceleration is going to be exactly this right here. I'm sorry, I need to divide by m to get my full answer. So that's part A. Next, we are told to derive an equation for the velocity as a function of time. And we're going to do that using separation of variables. So I'm going to say negative kv equals m, and now I'm going to write this as dv over dt. Let's go ahead and do separation of variables like we've always done. So negative k over m dt equals dv over v. Now I know this is where a lot of students who are in Calculus BC are taking a different approach than I am. So what I almost want to say is at this point, whatever you've been doing to do separation of variables, go ahead and do it. But I'm going to follow the technique that works for me. So I'm going to say negative k over mt plus the integration constant equals the natural log of v. And now let's plug in those initial conditions to get that unknown c. So negative k over m times 0 plus c equals the natural log of v naught. So continuing with the solution, I'm going to get negative k over mt plus the natural log of v naught equals the natural log of v. Now, given that we've had some practice in class, I'm going to go a little faster here. So negative k over mt equals the natural log of v over v naught. I'll exponentiate both sides, and then when we simplify, what we're going to get is that v of t equals v naught e to the negative kt over n. So this is the answer to part V. And when we sketch this, we're just going to get an exponentially decaying function like this. All right, so next we want to actually derive an equation for the distance the object travels as a function of time and sketch this function on the axes below. So now we want to get x as a function of time, and we're going to get that by integrating v. Number one mistake I see students do, and at this point, given that you've had some of this in calculus and you've had some of this in mechanics, what we don't want to be doing, so I'll just write the wrong answer here, and then I'm going to erase it. Do not do the following: x naught equals at plus v naught, and then try to plug that in. That is not how that's going to work. That assumes uniform acceleration. So this just does not apply. And we have an initial condition, which is that at time equals 0, the position is 0. So we're going to say x of 0 equals 0. So let's go ahead and actually integrate this function. So x of t equals v naught e to the negative kt over m dt. Now, for those of you in AB that haven't had this, just so you know, the integral of e to the ax, I mean, you can do a chain rule on this if you want, those of you in BC, but I just prefer to memorize that the integral is going to be negative e to the ax to the negative ax over a plus c. That's just an aside, and I'm going to use that here. So x of t is going to equal m v naught over k with a negative sign, e to the negative kt over m plus c. And now we're going to go ahead and solve for c. So we know that 0 equals negative mv naught over k times e to the negative kt over m, and I'll put 0 in for t, plus c. This will reduce to the number 1. So this gets us that c equals c equals mv naught over k. Putting it all together, we're going to get that x of t equals mv naught over k 1 minus e to the negative kt over m. So to go from here, so just to be clear, you will need to plug this back in for c. You will factor and simplify. So I'm just going to write here, after subbing for c, and simplifying. So I want to leave that exercise to you to do. If you don't factor it, the AP is totally fine with it, but this is the solution that we're going to write out. And whoops. So what that tells us is this is the answer that we have for part C. And now we're going to go ahead and write out the answer for part D. Well, let's make sure we graph this. So this is something where we are going to end up getting some kind of limit as we go to infinity. So one thing we want to do is let's just figure out how far the object goes. And so it actually turns out we should do part D before we finish up the graph. Let's put in time equals infinity into the equation that we solved. So that's mv naught over k, 1 minus e to the negative kt over m, and that's mv naught over k, 1 minus e to the negative infinity. It's really a limit. And this, of course, is 0. So we're going to get mv naught over k as our limit. So as t goes to infinity, x goes to this value. So our asymptote is going to look like this. This is going to be mv naught over k, and our position as a function of time will look like this. So the key here, this integral should be pretty straightforward. Solving for c gives you mv naught over k. So that little factoring bit is something that you should do on your own. I want to keep you awake during these videos. I don't want you just simply copying every little thing I do. I do want to see some active participation. So we'll get mv naught over k as our constant. We'll get this expression for x as a function of time. And as time goes to infinity, we reach this limit of mv naught over k. So that is number 1 on the 1990 AP. We'll take a look at the rest of the problems in future videos.